Thank you. So great to be back. One thing I forgot to mention before, and I know I don't have to, by the way, where are the, by round of applause, if you graduated in the last 10 years, 2008 to 2017, can you let me know where you're hiding? You guys seem really tired for young alumni. I'm expecting more from that. And the people for the 10 years before that, from 1998 to 2000, yeah. All right. Okay, to the young alumni, that's what happens when you have alcohol and caffeine. That can be you. And by the way, mostly to those people, but to everybody, to the extent that you are taking pictures with your phones, I understand you are part of the generation that does everything with your phone. So take pictures, tweet them, put them online, let everybody know what a great time you are having here tonight. Snapchat, I don't know what these things are. No, my kids are millennials. They're part of your group. They're part of this generation that does everything with their phone. The only thing my kids don't do with their phone these days is answer it when I call. No, then suddenly it's like, whoa, how did this talking app get on my device? No, it's strange because like if I want to know what's going on in my kids' lives, I'm supposed to text them. And I know how to text. But the thing is, I text like a baby boomer. I do. I like to spell out words and use punctuation in my text messages. And no, that confuses them sometimes. It does. All right, like last summer. I got tickets to go see the A's play because they've got this special deal. They need at least 12 people in the stands before they start, so you can get them cheap. And I sent my son a text. It said, to see if you get, it said, Theo, comma, want to go to the game, question mark, Dad. So he knows who it's from, okay? And the thing is, he basically said that this is the same thing as if I sent a message that said, my dearest son, Theodore. The heat has returned once again to the Bay Area. And yet my heart still soars with thoughts of our heroes at hardball. Our local champions are being challenged this night by those scallywags from the East. I've managed to procure tickets to this evening's contest. Shall I come by your abode in my horseless carriage at dusk? Eagerly awaiting a reply. Sincerely, Father. On this, the 14th day of the month of August, in the year of our Lord 2017. The thing is, my son's a big baseball fan. I raised my son right. He loves to go see baseball. And so he immediately sent me back a text that said, K. Okay. No, it's not. No, okay is too much. He didn't want to get carpal tunnel from all that typing. So just, anyway, tweet it out, send pictures, get that stuff online. That's great. Thanks for coming to the wannabe MIT class of 22. Welcome so much. You guys have a big choice. This is basically, your years in college is where you find your people. These are my people. I am so glad to be here. It is amazing. I talked to some of my friends about the fact that I'm coming to an event where we're going to discuss the existence of gravitational waves and the looks I get from these people. This is not something you can talk about with the Muggles. It's not. It's not that. It's a very special group of people. And the thing is, when we're all together like this, it is a very special event. Because in most of the time, you're not going to say this in front of other people, but most of the time when you are in a room, you are the smartest person in the room, right? And now, half of you are the dumbest half of the people in this room. and you're going, but it's not me. Yeah. Right, I never think I'm the best looking person in the room. I never think I'm the tallest person in the room. But yeah, it's, so this is an interesting thing. And we get to geek out about stuff. We get to talk, get excited about stuff. I mean, I was class of 1983. I'm a baby boomer. So I got really excited. Man went to the moon. I was 7 years old. That was amazing. We all watched it on TV. I had my brother stand next to it to just act so the antennas would be right. And, no, because I grew up in a household without remote control. I know that's hard for some of the young people to believe. My remote control was actually my younger brother, Lou. If we wanted to change the channel, I'd take a cookie, toss it near the TV, say, Lou, look, there's a cookie, and have him change the channel while he's there. So that was exciting. Science was huge back then. Everybody believed in science. And it started becoming disappointing. 2006, Pluto lost its status as a planet. I was crushed. I was personally crushed. Hashtag dwarf planets matter. No, all planets matter. I know. It's the beginning of the end. We live in a world now. We live in a world where most of the people we talk to are perfectly happy to accept a weather prediction from a groundhog. But they will not believe climate change from scientists. That's fake news. So this is a weird place that we are living in right now. And it is strange. It is just strange. I mean, again, we made it to Mars. We made it to Mars, and most of the people on TV are going, no, that's in a studio in Van Nuys, which is a weirder place than Mars. I don't know if any of you people have been to Van Nuys. It's, so again, very excited, just excited to be around people who want to hear this stuff today. That's absolutely amazing. Oh, by the way, before I forget, most important thing I need to talk about today, my youngest son, Eric, got engaged on Saturday. No, you cannot. It is, my brothers, I am one of 8 children. My parents thought they were part of the Irish Catholic branch of Judaism. So, but my son is going to be the first of my mother's grandchildren to get married. And my son, most important day of his life, most important thing he has done so far, he let me know by emoji. By emoji. What is wrong with you people? It would be amazing. Yeah, is there a talking app? No. So he sent me the emoji last Saturday. I am between comedy shows. I get the emoji from my son. I take a quick break. I immediately call my mother. My mother is so excited. This is great. I then get back to the show, and I realize after I do my set that my son has a different phone than I do and uses a different app. So sometimes the pictures he sends are not the pictures I receive. And now I'm starting to worry, is he really getting married, or did he just get his girlfriend a scarf? That would be, but it doesn't matter because I've told my mother, so either way, my son is now getting married. It's too late. My mom's already excited. My mom's already started making food for the wedding. It does not matter when, a lot of you may not understand the relationship that Jews have with food. A lot of people think being Jewish is about having a closer relationship with God or controlling the world's banks, and it's not. Judaism is really just an unhealthy food cult. That's all it is. 90% of Judaism is about eating things that will kill you. The other 10% is about making everybody else feel guilty they're not eating enough of that. So that's what we do. And my mom immediately started cooking, started making food, because my mom always believes that you never let a friend walk away hungry. Never let a friend walk away hungry. The last wedding we had in my family, my youngest brother Bill had been living with his girlfriend for 20 years and just decided one day they're going to get married. So they had a destination wedding, at City Hall in San Francisco. And it's a beautiful destination. It comes with the drunk guests all on the side already. And the thing is, they were doing it just for them. They're just for them. But they knew that they could not just sort of slip in, get married, and go back, because if my brother ever introduced his girlfriend as his wife in front of my mother, and my mother then found out that way, she would die on the spot. And there's not enough left in the will to make that worthwhile. So they told my mother, and my mother immediately decides she's coming to the wedding. She's crashing the wedding. And my brother lets me know when he mentions, by the way, we're getting married, that he goes, "You're not invited." And I'm okay with that. I'm fine. You know, I locked him in the closet when he was 4, so payback. And so he, but my mom, he goes, "Mom's coming. And by the way, Mom's staying at your house. She's coming next week." And I'm going, "Whoa, hold on." And he goes, "No, Mom said, you said she was always welcome at your house." And I said, "No, my ex-wife said she was always welcome at her house." But my mom made me crash the wedding, and it was a little weird, because my mom, even though we grew up outside of New York, my mom didn't really take public transportation very much. So when she came out here, I tried to put her on BART, and she was confused. The thing is, I went with her. We got on BART, and I know what to do on BART. I commute all the time. Okay, I got on BART, I went in the corner, I put a look of apathy and despair on my face, I pulled out my phone, and I started playing Candy Crush. I know what to do. My mother, on the other hand, started making friends immediately. And I know my mother's made friends because I started seeing people walk off the train with little brisket sandwiches in their hands. Because my mother never lets anybody walk away hungry. So my mother has started making food already for my son's wedding. We don't know when it's going to be. They haven't made that plan. But I immediately, my ex-wife is out of the country right now, so I let my family know. I let her family know. And they're all sending my son messages, congratulating him. And he is just ignoring all of them. And so they keep contacting me, saying, "What's going on? When are they getting married? How did he propose? There must be some amazing story. There's got to be something amazing. It is the most important day of his life." And I talked to him. And so my son actually did. He planned this out. He got the ring. And they went on a hike. They went on a hike in the wilderness. And they went to a clearing. And then I'm thinking, oh, this is great. He is being so romantic. His friends probably popped out singing, "I just called to say I love you." And little squirrels came with the ring and brought them up. No, none of that. He just sort of, said, "Hey, want to get married?" Handed her the ring. My son is an engineer, so no romance involved at all. His girlfriend, really, really nice, but she has no sense of direction. They are miles from civilization. I think she thought it was a threat. Basically, if you do not say yes, I'm not telling you how to get back. And so she said yes, they're now engaged, and it's great. They are so happy. So no, there's not some amazing story. This is what happens when you raise little engineers. My younger son is a mechanical engineer. He works for a failure analysis company. They break stuff. When other people break things, they try and fix it. He's been breaking stuff his whole life. He's a breaker savant. Now, one of those little kids that used to take things apart and tell me how they used to work. It is so great. I mean, come on. A lot of you must have been doing the same thing, right? Come on, we have engineers here. This is what we do. It is absolutely great. I don't actually do comedy full time. During the week, I work for a tech startup. Which is pretty common, I'm guessing, around here. You probably all realize that every startup in California is now required to have a grown-up. So I have job security. I think my title is now Dude. So it is really a lot of fun. everybody in the company I'm working for is younger than my children. So it is really like I'm running a daycare service. I'm the parent in charge of snacks. And that's, oh no, kale smoothies for you today. Oh, it is, I mean, there's a lot of energy. It's really exciting. They ask some really strange questions. Last year I got asked, when's the 4th of July? Okay, that's one child that was left behind. Oh, frightening. Oh, no, but they all seem to know exactly when Burning Man happens. That's the thing. For those of you who are over the age of 40, that is a festival up in the desert in the middle of nowhere that they head up to. And the company shut down, and they all headed up to the desert for this thing. They invited me along, but trips to the desert have historically not gone well for my people. I am not, we are not falling for that again. Oh, God, no. So frightening. It is. So anyway, we are about to get our speakers up here, and I'm going to introduce the person who is going to introduce our star for the day. I do want to make sure that I'm saying all the important stuff. Most of the thing I do want to mention is that first of all, our speaker is Surya Ganguly. He is going to be coming up. Got 4 degrees from MIT. 4 degrees from MIT. He got 2 Course 6 undergrad and a master's. Course 8, Course 18. By the way, for those of you who are not MIT alumni, no more words the rest of this session. He did some research at UCSF. He's now a professor at Stanford. He actually understands all the particle physics theories that are going on, at least enough to be able to sound like he knows what he's talking about. But the most important thing is that I need to mention is the picture that you see in here was from his OkCupid profile. It is great. And right, he is now married. So no, it's amazing how many people are doing this online dating thing. Another place where you have to absolutely find your people. It is. I mean, they've got all sorts of strange sites right now for fitness people. Farmers only. Farmers only. Find a hoe with a hoe. I don't know what this is. And no, I mean, I tried. I'm divorced. I actually tried online dating. And being Jewish, I was clearly attracted to one of the free sites. And so gave that a try. It's just, it is really hard when I'm 56 years old. This is not something that is easy for me. People my age are not, paying attention online. It's actually, I shouldn't. Right now, I'm working on myself right now. That's a nice way to say nobody's dating me. My girlfriend broke up with me. I put on some weight, and I'm trying to get back in shape. So, and the problem is I'm 56, so I get hurt doing nothing. No, I pulled a hamstring sleeping last month. So my doctor said, don't do that anymore. Trying to get back in shape. It is, it's going to be a lot of fun. Anyway, let's get time. My time is up. It is time for us to get to the reason you all are here, the reason you are all excited. So, ladies and gentlemen, to introduce our main speaker of the day, Surya Ganguly.
Thanks, Ira. Thanks, Ira, and thank you, my wife, for selling me out. In any case, It's my great honor to introduce, I'm not the main speaker by any means, it's my great honor to introduce Professor Nargis Mavalvala. She's a professor at MIT. Just to give you a sense of how amazing she is, I'll just tell you one of her main scientific achievements. Imagine that you have two mirrors 2.5 miles away from each other. Now the entire fabric of space and time is going to warp and bring those mirrors a little bit closer to each other. How much closer? 1/1000th the width of a proton, okay? So you have to figure out how to measure a deflection of two mirrors 2 miles apart to the precision of 1/1000th of a proton. Who are you going to call? Nargis. That's what's going to happen. She pulled it off, all right? She did it through some amazing work that we'll learn about involving really stabilizing the mirrors, making the very flow of light between the mirrors more precise. She manipulated light itself to measure gravity. It's pretty amazing. Just some background about her. She's a professor at MIT. She did her undergrad at Wellesley. She did her PhD at MIT. Her career took a real nosedive, though, when she was forced to take a postdoc at a really small technical university in the backwater suburb of LA called Pasadena. I forget the name of the university. But, you know, she managed to recover pretty well when MIT hired her back as a professor. And now she's, now she'll be on stage. She's the winner of many, many awards, in particular the Macarthur Genius Award. So given, congratulations. So given that she was able to stabilize these mirrors and she won a Genius Award, unlike our president, she really is a stable genius. All right. So without further ado, why don't you come up? Thanks, it's great to see you. Congratulations.
Thank you.
So, grab a seat. So Nargis, it's wonderful to have you here. I've been really looking forward to talking to you. So this LIGO mission that you've actually been at the culmination of, it's really been a 100-year odyssey, right? When Einstein just dreamed out of his head gravitational waves, general relativity, black holes, space and time. Then the NSF started 40 years ago, spent $1.1 billion, and you were there, like at the end when you guys discovered the gravitational waves. So let's start at the beginning, right? What did Einstein dream up out of his head? What is space, time, black holes, gravity, and gravitational waves?
Wow.
You could give us a tutorial.
So first, hi everybody. Thank you for being here. This is very embarrassing to have all these nice things said about me, but now I can talk about the things I really like to talk about. So so let's start. 100 years ago, Einstein came up with his theory of general relativity, which is really a theory of gravity. And it sort of superseded everything. So how many of you have at some point in your life taken 801? Okay. Let me tell you, we lied. Gravity is not a force. Yeah. So Einstein's idea of gravity was, in fact, that gravity is curvature of space-time. And he essentially solved an age-old problem that Newton left us with. Newton said gravity is a force, and Newton was puzzled, why do planets and stars, say the Earth and the Moon or the Earth and the Sun, why do they attract each other? What causes that attraction? How do they know about each other? This is the problem of an action at a distance. Einstein came along and said, never mind the force picture, you can forget about it. Space-time curves when you put something heavy in it. And it's anything else, any other piece of, any other mass has to follow that curvature of space-time. So it's very simple. You take a trampoline, put a bowling ball in the center, curves. Now, the thing that was kind of Einstein's idea, and that was beautiful. Then Einstein asked another question. He was like, what happens when you take this massive object and you accelerate it? So in the analogy of the trampoline, what if you took the bowling ball that's in the center of the trampoline and bounced it up and down? And then he found in his equations, out popped these waves, a time-varying part. And I have to say, he was very unhappy about it. Yeah. So in his original paper, he kind of looked at them and he dismissed them. He said, well, they'll never amount to anything. And then later, 20 years later, he actually wrote a paper whose title was, "Do Gravitational Waves Really Exist?" And if you read the abstract, the answer is no. And
Einstein was wrong, she was right.
but no, then he submits this paper, the retracting gravitational waves, and he retracts the retraction, and then he goes quiet on the subject. So he actually was ambivalent about them, doesn't say anything more about it. Then out of the same ideas of space-time comes the idea of a black hole. That came 3 years after his 1916 paper from a physicist by the name of Schwarzschild. And Einstein didn't like those either. He kind of felt like nature would never do something so ridiculous as to put so much gravity into a small volume, so much mass into a small volume that even light can't escape. So that was another thing that he kind of dismissed as unnatural. Now, he was pretty justified in thinking those things because we didn't really discover, as scientists and astronomers, black holes until well after he was dead. So it's reasonable. But so gravitational waves are ripples of space-time. If you think about space-time as the surface of a pond, and if you drop a rock on the surface of a pond, you see ripples that spread out. That's what gravitational waves do, except there's no pond, it's empty space, and there's no rock. It has to be really substantial objects like black holes or the cousins of black holes, which are neutron stars. Okay, so that's what Einstein told us. Now, there's another piece that most of you must remember, maybe if not from 801, from 802, we teach you that gravity is weak. And we even make you do a little calculation to show how much weaker than electricity and magnetism it is. Does anyone remember the answer from your problem set number 1 in 802?
I don't. Somebody please answer.
Yeah. So many orders of magnitude weaker, and therefore this effect, the ripples of space-time, are also very, very faint by the time they arrive here on the Earth. And that's part of why it's taken 100 years to go from this idea that Einstein gave us to actually making a measurement. And there was many discoveries along, many discoveries had to happen along the way. So let me tell you what they were. A laser had to be invented. That happened in 1960. Black holes and neutron stars had to be discovered. That happened in the late 1960s to early 1970s. And another important thing that had to happen was Einstein, look, we all learned Newton's law, right? It's such a pretty little equation. Now, Einstein also wrote a very pretty equation, except that it's the most beastly equation ever written. And it's very, very hard to solve. And so the last piece of thing that we needed to get in place was computing power to solve Einstein's equations numerically. And you put those three things together, and the most nearest and dearest to me, you have to actually invent the technology for making a measurement that's 1,000th the size of a single proton.
Yeah. So let's talk about that actually. So, yeah, how did you do it? Like, what did you have to do to like figure out whether these mirrors would just? Well, first of all, could you explain kind of what a gravitational wave looks like and why it should cause mirrors to deflect a little bit?
Yeah, so before we can talk about mirrors, we have to talk about why do we even bother using mirrors. So what does a gravitational wave look like? What does it actually do here on the Earth? At the source, typically a source of gravitational waves is some very massive object like a black hole or a neutron star orbiting another black hole or a neutron star and colliding. That's the kind of sources we can hope to detect. So this gravitational wave is emitted out at the source, and if we were anywhere near there, we'd be ripped to shreds and it'd be terrible. So we don't do that, we're far away. Now along comes this gravitational wave, and as it passes through a region of space, it basically shrinks and stretches the space. So if a gravitational wave passed between the two of us, ever so slightly we would move a little bit farther apart and then a little bit closer in together. And we'd keep doing that at the frequency at which the gravitational wave is coming by. Now, it's not just that we move apart or closer together, it's got a geometry to it. And the easiest way to demonstrate that geometry is actually to dance.
Let's do it.
Shall we do it?
Let's do it. So she invented also the gravity dance. And
I was not the inventor of the gravitational wave dance. I've just
you perfected it.
Thank you.
Yeah.
You're right.
All right, so we're going to, I actually don't know the gravitational wave
I thought
dance.
you were going to do it with me.
I will. So you're going to teach
Okay.
me.
Okay, here we go.
Okay, so here
you
we go.
stand.
Let's see. Okay. Do I need to stretch?
A little bit,
A little bit.
because
1/1000th of a proton.
well,
like that.
really what happens is you
Yeah.
have to stretch because the gravitational waves we detect, the oscillations are going at 100 times per second, so you have to
Oh,
kind
God.
of,
I have the same problems you do. I have to, yeah.
Okay, so what does a gravitational wave do? It's somewhere out in the universe, it's come and it's going right through me, say, and it'll go through you and all of us. So you start off as a cross,
All right.
okay, but with your arms are in
Uh-huh.
and you're standing tall. Now when the gravitational wave comes by, it's going to squish you downwards and make you wider.
Okay.
That's the direction we don't like.
Yeah.
But in the other half cycle, it makes you taller and narrower.
Yeah,
Okay,
okay.
so, ready?
Yeah.
Okay, so arms out and there you go, that's it.
Oh, interesting.
And that's going at once per second.
Yeah.
So that's when the neutron star or black hole is far from its companion.
Uh-huh.
As it gets closer and closer and closer and closer and closer and closer and closer.
I'm out of phase.
Exactly. And then it speeds up.
Oh, okay.
Okay, so that's really what it's doing. And that's a really important thing to know because that idea then taught us how we might measure it. And the person
cool.
who gave us that idea, by the way, was MIT Professor Ray Weiss, who was also my PhD advisor and also the 2017 Nobel laureate. So he had the idea that if it's motion in that way, so here's a simple thought experiment. Imagine I'm a laser and you're a mirror, and you're a good mirror. So you obediently.
You already screwed up now.
You better be a good mirror. So you obediently reflect light back to me. And if I have a really good clock, I just measure the light travel time.
Right.
If a gravitational wave passed through, it would change the distance that the laser beam had to travel, and it would change the travel time, and we could measure that. So that's the simple idea. And that, in fact, in principle, that would work, except that the precision you need for the clock to make that kind of measurement, we simply don't have. So he came up with a different idea, which is to use two laser beams, and you shoot them out in an L shape. So one is going up and down between our toes and our head, and the other one is going between our arms. And that way, when one direction gets shorter and the other one gets longer, the light travel time of one beam is different than the light travel time of the other beam. And when they come back together, the waves will either be in phase and give you lots of light, so the peaks and troughs line up, or they'll be out of phase and they give you no light or everything in between. And that's called an interferometer. That's the I in LIGO. All right, so that's what he invented. Now, he was also invented another really important thing. He understood that you couldn't make this measurement unless you made the detectors very long. Now, why does the length matter? It matters because the amount by which the space between us changes as the gravitational wave comes by is proportional to the distance between us. So if a gravitational wave of a certain strength came by and moved us our distance by some amount, if I moved to the end of the stage, it would move that distance by double the amount. So the farther apart the two objects are, the better. So he understood that. So he proposed that we should make these 4 kilometers long. And when you do that, you have the job of measuring changes in the distances between the laser and the mirror of 10 to the minus 18 meters, which for people who don't think in those terms is 1,000th the size of a single proton. And so he thought, well, that should be doable. And he proposed this in 1968. And it took us that long from the time he gave us the idea to do it was another 30 years.
Yeah. So how did you?
Years,
so you're being modest because you played a critical role in kind of making that happen and inventing the first detector, right? So what did you do, and like how did you stabilize the mirrors? How did you make the flow of light more precise?
Yeah. So let me be clear. I'm not being modest. This was the work of really hundreds of
She's
people.
being modest.
So I had my piece in it,
Sure,
but there was a lot. So what do you need to do to make a measurement like this? So the first thing we need to do is everything here on the planet moves the mirror by much, 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 much more than the gravitational wave does, right? So if I just plop a mirror down on this table here, does anybody want to guess by how much it would move just from being in this environment? Do you want to guess? You're a theorist. I don't know if you.
I don't really know numbers. That's like this much?
Yeah. So
I didn't do that well in 801.
someone said it. A micron. Yes. 10 to the minus 6 meters. A thousandth of a
That
millimeter.
was what I was going to say.
Yeah. Very good. Okay. Now, so it moves by a micron, and yet the gravitational wave would move it by 1/1000th of that. So we have to stabilize it and shield it from these vibrations by a factor of 1 billion. And the way you do it is actually, it's a very, very fancy, glorified shock absorber, if you will. It's like the shock absorbers in our car, but it's a big vibration isolation system.
Can I buy one?
Yes, you can.
How much is it?
For a few million.
I spent too much on that table. Anyways.
Yeah. I mean, a few million and a bit of time, because we can't churn them out very fast. Okay. But this is one of the things that's really fantastic about working on an experiment like this, is you can buy nothing except the tables and chairs you sit on. Everything else you either have to invent or work with someone who's an expert to do, right? So that's the first thing. You have to make the mirrors very still. Now imagine you succeeded at doing that. You've vibrationally isolated your mirror, you've put it in a vacuum, it's not being shaken by air currents, it's not being shaken by earth vibrations. That would do you no good if you didn't have a way of measuring the position of the mirror. And so, the measurement is done by using the laser. The wavelength of the laser light is the tick marks of our ruler, if you will. So now comes in the next horrible factor of 1 billion. So the laser light we use is near infrared. It's close to visible. So its wavelength is also, turns out, just coincidentally, it's a micron. So 10 to the minus 6 meters. And yet the measurement we want to make is 10 to the minus 18. So there's another factor of 1 billion. So it's basically what we are saying is, if I give you a piece of paper and I say, please measure its length, take out your ruler, and you'll measure it to the precision of the tick marks on your ruler. What we're saying is measure it to 1/100000th of a tick mark, right? And so that's what we had to do. And the way that you do that, it turns out, is you play a statistical game of using lots and lots and lots of photons, so you average over the tick marks, if you will, over the fluctuations of the tick marks. And that's the game that we play. So the laser.
So you have to have a bright laser.
So you have a very, very, very bright laser. And so that was the
cool.
game. So you do those two things and then a few other things, and you've got yourself a measurement.
Nice. We'll skip the few other things. I suspect that's really tough. Let's talk about the first detection event, right? That's an incredible story in the history of humanity. So using your device, you figured out that 1.3 billion years ago, two black holes, each of which are 30 times the mass of the sun, are spinning around each other. They collide at half the speed of light, and they emit 3 suns worth of mass energy of gravitational waves. And because of your interferometer, you see a light kind of going up and down a little bit,
right.
And you figure that out, right?
Yeah.
What was the mood like of the scientists when they figured that out? Did they immediately know what they were looking at? Were they worried they made a mistake? How long could they keep silent about it? Were there leaks to the press? What was the human element of that story?
The human element was that we measured this first signal in September of 2015, and we're roughly 1,000-person collaboration, and I think with no exceptions, nobody believed it. Okay. We all thought it was either a mistake or it was some maliciously injected signal. So one of the things we do, and this is done in many experiments, is we check ourselves by actually injecting fake signals into the data. And so the first thing that everybody, including myself, thought was, it's a blind injection. So you do it blindly. So you inject fake signals into your data to test if your signal finding algorithms will find it.
So do you have like a red team and a blue team, and
the
red team is doing fake injections and they try to fool the blue team?
You do, except that the red team is this very small and devious group of only 3 or 4.
Were you part of it?
No, I was not part of it. I'm not devious enough. And then everybody else who's involved with the analysis of the data are trying to check that out. But so it took actually several weeks. It was very quick to determine that there wasn't an injection, because we know which channels are used for that, etc. But then it took 2 more weeks or so to check that there wasn't something unintended and or malicious, intentionally malicious, or just some instrumental glitch or something else. And so it took, actually, the way I like to describe it, there was sort of mounting excitement. It wasn't this instantaneous, wow, we've seen it. It was like, check that, it's closer, it looks like it could be true. Check that, okay, check that one off, check that. It kept mounting. And so the signal was detected on September 14 of 2015. And for me, an important thing happened in early October, where we finally had checked the last thing and had done sort of the most due diligence you could do. And then it became real. And then we went into high gear for actually writing the paper. I can tell you, it is the most impossible thing to write a paper with 1,000 people. So,
I have a hard time writing it with 4 people.
Yeah, right, so you know what it means. And so then people again break up into teams. There was the paper writing team, and there was
did the public know that you were writing this paper?
Well, there were lots of rumors. I don't know if at the time, and so there's this question of why even keep it a secret? Once we were sure, why not just tell? Well, we were sure that it was real, but there was still a lot of work to do to come up with the final numbers you quoted. You said, well, we what were the masses? And you couldn't just say, hey, people, we saw something.
Yeah.
You had to say, what did you see? And that was a lot of work in getting that nailed down, getting the systematics nailed down, etc. So we were not just being, surreptitious. We were actually, doing real work to nail the physics and astrophysics down.
I see, that's excellent.
So,
what really impresses me is how incredibly precise physicists are when they do experiments. I mean, I do biology now, and we don't really know what we're doing, and we don't. Anyways, but the doctors in the room know what I'm talking about. But there was a recent observation that you guys had of these 2 neutron stars, right? That each one's about the mass of the sun, but it's only 12 miles across. So 1 teaspoon of neutron star is like 1 billion tons, right?
Right.
And this was this amazing event where they crashed into each other, they released gravitational waves, and you saw the light.
Right.
So you see it through 2 different lenses, right? And I think a whole bunch of observatories, light observatories, there's many more of those than gravitational observatories, all work together to collect the data. So what did you learn about the neutron star collision from these 2 different sources?
Yeah. So the first thing to say is that neutron stars are sort of the lighter cousins of black holes. Both neutron stars and black holes are born when an ordinary star like our sun explodes. If the parent star was heavy enough, so 3 times the mass of our sun or more, it will collapse into a black hole. If it was lighter, it sort of stops short of becoming a black hole and scrunches itself into a ball of neutrons. And so that's how they're born. But the important difference is that a black hole gives off no light, it's black. Neutron stars, because they're made up of neutrons, when they collide, they do give off light. So when they're just sitting in isolation, they may not give off light. But when they collide, you'll see a big light show. So when we first detected the black holes in 2015, you could point telescopes, and people did half-heartedly, but no one was really expecting to see anything. With neutron stars, you were expecting to see a lot of light. So we saw a pair of neutron stars with LIGO, and LIGO's has a European counterpart called Virgo. And so these 3 detectors saw gravitational waves, and we knew quite quickly that it was a neutron star just from the way the signal looked, because they're lighter, they have a different shape in our signal, in our detectors. So, and then very shortly after that, 2 seconds after that, a gamma ray telescope saw the signel as well. And so
why did it take 2, don't gravitational waves and light waves both move at the speed of light? So
they do. There's a couple of reasons for that. The one is that the gravitational waves their matter is very transparent to gravitational waves. And what that really means is gravitational waves they've passed through everything. So they passed out of all the material of the neutron star right away. The photons, the light on the other hand, scatters and interacts with the material, so it takes a little bit longer to come out. So that's somewhat expected. So the gamma rays came out, and because LIGO and Virgo were operating together, we were pretty quickly able to say that this event happened in a patch of sky that was in the southern hemisphere. And it was a pretty big patch of sky. It's about 30 square degrees. And telescopes do not like to look at 30 square degrees. Their field of view is usually a tiny fraction of a degree. So to cover a patch that's 30 square degrees would take a telescope quite a long time. It has to tile over a big patch of sky. But that, by gravitational wave standards, a pretty well localized source. Now it turns out, this is pretty fun, it was in the southern hemisphere, and when we saw the signal, it was daytime there. So no telescope could point anywhere and hope to see anything. Yeah. So the astronomy community had, the telescope community had something like 12 hours to prepare. And so 70 telescopes across the southern hemisphere lined up and were ready to point and start to tile that patch of sky. And within hours, actually, I think the first one was within 40 minutes of tiling. In that third tile, they picked up something. A new source had lit up. It was in the galaxy NGC 4993. Did you know that?
I did not know that. No. Please don't ask me that question again. I'm kidding.
Yeah. And so they saw that it had shown up there, and there was incredible amount of information.
How far away is that galaxy?
Yeah, so that galaxy is about 100 million light years away.
Oh, it's pretty close.
So by astronomical standards, very much. In fact, that first black hole we saw was 1 billion light years away. So this object was closer.
Is that why the signal was so big?
That's part of why it was bright and could be seen by many observations. So over the period of that night was really spectacular, but then over a period of days and weeks, many other telescopes with different colors and wavelengths of light picked up signals. And by looking at what point in time the different wavelengths of light light up in this object, we could tell what was going on inside of it.
Oh, that's awesome.
And what you saw, and this is what I think is one of the most beautiful results in my opinion, is we saw for the first time gold being made. Gold and platinum were being fused. So one of the long-standing mysteries that we've known about is, where does the gold and platinum here on the Earth come from? We know that all elements, the Earth does not make elements. All elements come from the stars and from star material that was existing when the solar system formed. And what's that? You do, but nothing that stably kind of populates the Earth, right? And the other thing is, in accelerators you don't fuse.
Take that.
Yeah. So how do you build up the heavier elements? That was the question. So if you look at our own sun or stars like it, you can make elements that come up to 56, iron 56, and then you just don't have enough neutrons to fuse bigger nuclei. And so we've had this mystery of, where do the heavier nuclei come from? We know some of it comes from explosion of stars, but still not everything we see. And now we saw that this collision of neutron stars, the heavier elements were being fused. And in fact, gold and platinum and the heavies. So it solved something that was a really decades-long mystery that astronomers have sort of wondered about. And so that's why these objects, these colliding neutron stars, were, after this event, were named nature's gold mine.
Oh, cool.
So
next time you go to a jewelry store, just say you want the gold from the neutron stars. They'll know what you're talking about. Yeah. That's amazing. So what fraction is from neutron stars? What did you know? Like all the gold on our planet.
Yeah. So I think something like only a third of it was accounted for before
Oh,
we
wow.
knew that these were, and there had been, of course, conjecture that this could be one of the ways, because you need a neutron-rich environment,
Yeah.
and neutron stars are such a thing. So people had suspected that it could be, but this was the.
So where do the protons in the gold come from?
Those are actually just by stable decay. They
I
form
see.
right there.
Okay.
So,
Okay. Oh,
yeah.
very cool. So every time humanity has opened up a new window into the universe, we've discovered completely different things that's changed our concept of the universe, of society. Like, for example, when we invented the light microscope, we saw all these critters moving around in water, and then we realized that our diseases came from germs, right? So it led to the germ theory of disease. So now you have opened up a completely new gravitational window into the universe. What's the long-term kind of future of gravitational astronomy? What can it teach us about the origins of our universe and its contents? Where is this going in the long term?
Yeah, so that's a good question. So in astronomy, just in the same way as with the light microscope, every time we've looked into the sky with even a new wavelength of light, we've discovered objects we didn't know were out there that are in the sky that nature makes. And I suspect that this will be no different. In fact, it could be even more spectacular, because we're not just looking at a different color of light, light is generated in processes that involve charge and matter. But here, where we could be looking very well at things that have a lot of mass but don't have properties of emitting light. Black holes are just one example. So I think there will be really unexpected, unknown things are very likely to.
And I hear they might be building another gravitational wave detector in India. Is that?
Yeah. So that's actually a LIGO detector that we hope to install in India. So one of the ways in which gravitational wave detectors are there's been lots of very poetic analogies of gravitational waves to the sounds of the universe, or listening to the universe. And they come about in part because the signals that we see with detectors like LIGO happen to be in the human audio band. It is by no means a sound wave that's propagating through the vacuum of space.
Yeah.
What it is it's when we encode that into a signal in our detector, and then you play it on a loudspeaker, you could hear it. And that's why we call them listening to the universe. And the analogy goes a little bit farther, which is kind of important. What it is, if you can do this experiment yourself. If you take 2 points of light some distance away, just at the end of the room, and if the lights flicker on or off, your eyes can very well resolve which did the left light go on or the right light go on. At the same time, if from those 2 points you play sound, your ears cannot resolve very well whether it came from the right spot or the left spot. And gravitational wave detectors are kind of like that. They're kind of like ears. They don't resolve very well where the source is. It's done by triangulation.
Yeah.
And therefore, the more of these you have that are far apart on the Earth, the better you can localize the source. And now we know from this neutron star discovery that localizing is very important.
Yeah.
If you want to point telescopes, you've got to know pretty well where it is. And so putting a detector in the southern hemisphere or in India would be very helpful.
Yeah, excellent.
So,
I just was visiting India, and a lot of scientists there are very excited about that possibility.
No, we are too, because it would really open up the kind of science we can do.
Yeah, that's excellent.
yeah.
I wanted to turn more to your personal stories. So, when I sit around at my applied physics faculty meetings, the demographics are such that you have a bunch of old white guys. By that I mean like 60 years old. Then you actually have a bunch of young Asian guys, actually, to be honest with you. And by young, I mean 40, young is always by definition what age I am. Which that's an interesting demographic shift from old white to young Asian. But unfortunately, it's mostly men. And you're a complete iconoclast, right? You're a woman of color, and you grew up in Pakistan, and now you've become a scientific leader, a professor at MIT, Macarthur Genius Grant winner. What was that journey like? What inspired you? What were the obstacles? How did you get from point A to point B?
Yeah, that's a great question. I'll tell you that when I think about it for myself, I'm kind of amazed. I was just doing what I love to do. Mm-hmm. I was given opportunities that many don't have, and somehow here I am. So,
What do you think your greatest obstacle was?
I think certainly, there's lots and lots of issues around gender, and I know they're there, and I work on them, but that was not my experience. I actually was always supported by amazing mentors, mostly men, because that's who physicists mostly are. But no, it was just I had a lot of support. I don't think that's universally true. So for me, I think my largest obstacle to being a good physicist is I'm not all that good at math.
Math just gets in the way. Yeah, totally. It's all about that intuition. Actually, you have that in common with Einstein. Einstein never said that he was good at math.
No, he was actually rather not very good at math, but he knew a lot more math than I do. But I want to say, something interesting about that sort of whole gender piece too. So, when we think about the LIGO and it was started by Ray Weiss, who's now 85, and the other Nobel laureates. I mean, it's not lost on the young generation that these Nobel laureates, all of them, whether they were physicists or from medicine or physiology, these are all very, very silver-haired white men.
Yeah.
And I just want to say to the young people in the room that it is changing. And in fact, when you look at who are the people who worked with these older men to make LIGO work, there's a lot of women and younger people. So you don't have to be, a silver-haired white male to be a good scientist. Please know that.
Absolutely. Actually, I'm happy to share with you, I was on the admissions committee for the Applied Physics Department at Stanford, and we were extremely happy to admit 50% women. Like it was even across the board.
Good for you.
And there's no affirmative action, nothing. We just admitted the best, and 50% were women. We were very excited about that.
Fantastic.
And we're trying hard to recruit them when they come
Right.
very soon.
We're gonna steal them away.
Well, we'll see. We'll see. We'll see. Oh yeah, I'm not on home territory.
I think I was going to say I have a room full of support here for that.
I have divided loyalties at the moment. Anyway. All right. So we have a lot of, a lot of parents actually told me, how do we get our children to be like you? We have.
My parents would tell them to choose another path.
No, well, we have a lot of, great parents in the Bay Area who have, very happy kids growing up in the world of technology and so on. But you have this abiding passion for the ethereal sort of structure of our universe. And in general, you have passion and curiosity about the world and about nature. What advice would you give to Bay Area parents to instill that same sense of passion and curiosity in their kids?
See, I'm no expert at how everyone should parent, but I'll tell you my own version of it, which is I kind of feel like our kids are born with innate talents, and the best thing we can do is to cultivate those and get out of the way. So to parent with a light touch. Yes, they need a little bit of guidance, and occasionally they need a slightly stronger nudge in certain directions. But let them do what they love. And if I'm a scientist, and if my kid decides that he has a passion for art, my job is to say, you go. I was going to say you go, girl, but I have two boys.
I see. Excellent. So yeah, that's like so I'm starting to see. We wanted to. Give the audience an ample chance to ask questions. I see questions showing up. Oh, excellent, on Twitter. So let's go down these are all my friends. Okay, well, let's start with you, know-it-all, Zuli. Do you, this is an adversarial question. It's all about applications. Do you envision other applications of the techniques invented to detect gravitational waves? If so, what are they? Zuli's like that. Don't worry about him. Yeah. He wants technology spin-offs.
Yeah, so
He's a cryptography guy, just so you know.
let me give you a fun story about something that already happened. So when we were building the first LIGO, we were looking for a laser that was powerful, so could put out lots of wattage, but was also very stable. Okay, because remember the wavelength of the laser light is our tick mark. And so there was a new technology for a laser that was invented actually here at Stanford. And the group that invented it started a company, and LIGO worked with them to develop this laser for LIGO's purposes. But it was, of course, a pretty nice laser, and so they also spun it off, and it became kind of a product that they would sell mostly to anyone who needed precision lasers, so research labs all over the world. Now, this laser was a solid-state laser, which used diodes to actually pump the lasing medium. And part of what they had to solve was a particular diode handling technology to avoid contamination. And so they sort of developed this diode handling technology, and then some years later, they were humming along as a laser company, and they got bought out by JDSU. Now you'll say, why would JDSU want to do that? JDS Uniphase is a big telecom company. What do they care about a precision sort of laboratory class laser system? They didn't give two hoots about the laser. They wanted the diode handling technology. So they bought the company, they spun off the laser division. You guys can go sell your little laser. We want the diode handling technology. So that was one of the ways in which you can see, that's just one of maybe dozens of such examples I could give, where, like I said earlier, when you're making a measurement at that precision, you're inventing everything along the way. And so there's been lots of such things.
Great. I have a question from Atul Bhatt. It's amazing how large the universe is, that we're only seeing relatively few wave events. So is there a way to estimate, given the size of the observable universe, can we estimate how many neutron star or black hole collisions there should be, say, per cubic parsec per time?
Absolutely. Yes, there is. And it turns out that what we're seeing is sort of consistent with those estimates. So what you can say is we know how many stars are out there. Of those stars, we know how many we expect to be, and these are all estimates, we expect to be black holes or neutron stars. Of those, we know how many we expect to be in binaries or pairs. So one of the things that we didn't say is, if you just have a star or a black hole or a neutron star, whatever, just sitting around, it doesn't radiate gravitational waves. It has to be accelerating. And that means it has to be in an orbit of some sort. And so that means a binary. So once you go down this line of reasoning, how many stars are there, how many are black holes, how many are in binaries, and then also we don't see the binary throughout its life. A binary black hole system may live for 1 billion years. We only see the last few seconds of its life when it's close enough before it collides. So once you take all of those things and you put it together, it's very consistent that with the sensitivity we have, there's a certain volume of the universe we can see. And within that volume of universe, we should be seeing something of the order of a black hole collision every few months, and that's what we've been seeing.
Oh, wow.
So it's pretty consistent with the estimates that come from these fairly first principle ideas of how many objects are out there.
So every month you guys will see, on average, you'll see an event.
Yeah, so what we didn't mention, but we've seen now we've seen 5 black hole collisions and 1 neutron star. So.
Very cool.
The neutron star numbers are of course fewer, just because they're lighter.
They're smaller.
So because they're lighter, the amplitude, the strength of the wave is smaller.
So they have to be close.
So they have to be
to
close
see
in,
them.
exactly.
Yeah. Great. So a friend of mine, Jonathan Goldman, is asking a question. It's awesome to see these measurements of gravity at a massive scale. What are your thoughts about measuring gravity at a small scale? It seems like these experiments might be easier to do, and in comparison could reveal new physics. For example, my colleague Aron Kapitalnik at Stanford is doing these tabletop gravity measurement experiments. So how does that compare?
Yeah, so they're completely different beasts. And let me tell you why. These experiments of measuring gravity at close distances are basically testing deviations from Newton's law. Is the gravitational force really go as 1 over r squared at smaller and smaller distance scales? And that is what I would call static gravity. Gravitational waves are the dynamic part of gravity, and nothing in those experiments has any wave or dynamical part. So it's really, really different. In fact, we know of no way to make a gravitational wave. Nature has to do it because it has to be objects like neutron stars and black holes, extremely dense, compact objects. So, unlike light
So if
waves,
I jump up and down really fast, I can't pull it off.
You would, except that they're immeasurably small.
That's too bad.
At the Planck scale, right? Exactly.
Yeah, thanks. I have lost a little bit of weight, but not that much.
Yeah.
Still working on it.
Yeah. You'll have to collapse into a black hole first, which means you'll be
I feel like that happens
submicroscopic.
So Shuja, ever the investment-minded entrepreneur, what will be the next big discovery, and where is the most focus for the LIGO team now? He's asking the VC question.
Yeah, so the focus for the LIGO team right now is that we are actually, the detectors are off the air. We're putting in a few...
You're not getting any money from Shuja then?
No, he'll like the answer. Yeah, so
Okay,
we're putting in new, a couple of new subsystems to make the detectors have greater sensitivity so we can look farther out. So look, I think what's inevitably going to happen is we'll continue to see black holes farther and farther out as we improve the detectors. We'll continue to see neutron stars, and so I think that's kind of going to happen. There's another source that we have a good chance of seeing are supernovae, which are exploding stars. They're quite rare, and we're only sensitive to them quite nearby, so there's not going to be a high event rate. Personally, I think the next big discovery, the next most exciting thing that you guys could hear about is some kind of headline that says gravitational wave scientists discover an object and they have no bleep idea what it is.
Exciting.
So that's really the promise of what we've done. Look, I think the celebrations around black holes and neutron star binary mergers are appropriate. But those were things we kind of knew were out there. We've never seen them before, so they're still beautiful, and we're learning new things.
Right.
But there's all this stuff out there that we probably don't know of. So could it be, I hate to say it, could it be a wormhole?
Exciting.
Do
you think that might happen? That we might? What would a wormhole look like from the perspective of?
I think you have to very much more precisely map out a space-time.
Could you tell us what a wormhole is?
Oh, a wormhole is basically a wormhole is the black holes cause. So one of the things that's kind of amazing about what Einstein did to our thinking of the universe is we were used to thinking until he came along of thinking of space as kind of this empty, placid phenomenon. And he told us that space can curve. You put a massive object there, it will curve. He told us it can ripple. But with the introduction of black holes, his theory tells us that it can also tear. So what's at the bottom of, you've seen these famously drawn space-time diagrams of funnels under black holes. What's at the end of the funnel? So mathematically, we think it's a singularity. But you can imagine that what it is basically a tear in the fabric of space-time that opens perhaps into a parallel universe. Now, these are very space fiction-y ideas, but there is nothing mathematically forbidding them.
They're consistent with Einstein's
absolutely,
equations.
Exactly. And so it's not crazy to think about those things. And what would be the effects that we could see here would be very close to the horizons of black holes. Are there effects that we could measure that tell us something about what's inside of them? And that's very hard business because you need to very precisely map out the whole space-time around the black hole, not this very sort of crude estimates we're getting right now of sort of large-scale waves.
I see. Excellent.
But there's one other thing that we haven't talked about that I think is perhaps the most amazing thing gravitational waves could give us. You know, we'll celebrate black holes and neutron stars. Really what they've done is they've given us a new way to look at the universe that doesn't involve light. And there is one source that's, to me and to many of us, beyond everything else. So we believe the universe began with a Big Bang. And it was, so when the universe was hot and dense, the photons were trapped inside of that. Photons interact with matter. Every time they meet a particle, they either scatter or absorb from that. So when the universe was hot and dense, the photons were just trapped inside of this hot, dense soup, scattering about. Gravitational waves, on the other hand, they're extremely aloof. Their matter is transparent to them. They come streaming out. So when we look back at the first photons that we can see, the earliest photons that escaped the hot, dense soup of the universe was when the universe was 400,000 years old. Whereas the gravitational waves have been streaming to us from t equal to 0. So if you could see these primordial, these early universe gravitational waves, you're looking all the way back to the Big Bang. And there's nothing else that can give us that information. So that would be incredible. Now, the problem with it, and that's why we haven't talked about it as much, is that these are very faint. In fact, we would need detectors that are 1,000,000 times more sensitive than the ones we have today. So I'll go out on a limb and say I don't think it's going to happen, at least with these kinds of detectors. It's not going to happen in my lifetime. But you know, class of 2022, we're looking at you.
We gave you some money, so you know, like, we want some return. Yeah. We want to see into the very beginnings of the Big Bang, not with photons, with gravitational waves.
Right.
All right, excellent. On that note, I think we're running out of time, so let's thank Nargis for opening up.
Thank you. Thanks very much,
you.
everyone. That was fun.
That was awesome. Nice job. That was
Well
great.
done.